here we have the two friends, Mr. Voss and Mr. Cole. They bowl together every Tuesday night. It tells us that their scores are both approximately normally distributed, and it gives us the mean and the standard deviation for each one. And so we're going to assume that their scores are independent. Here we want to find the probability that Mr. Voss scores higher than Mr. Cole on a randomly selected Tuesday. So how I like to start to think about this is seeing if we can use the information from the problem, start to represent it mathematically. So we want to find the probability that Mr. Voss is going to score higher than Mr. Cole. And if we use maybe a B to represent Voss and a C to represent Cole, if we were to get the pieces together on one side, it would end up looking like this. If we were to subtract Mr. Cole's score from both sides, what we're really trying to find out is the probability that the difference between the two is greater than 0. And so this was back in 6.2. So here we're going to be thinking about our rules for combining random variables to figure out that difference. And so we're going to go back here to look at information from the problem. So it says that Mr. Voss had a mean of 212 and a standard deviation of 31. So we might just write that off to the side here with some labels, so we know that that is all for Mr. Voss. And then for Mr. Cole, he had a mean of 230 and a standard deviation of 40. All right, and because these are normally distributed, we are eventually going to be using a normal curve here to find our answer. When we are doing our labeling here, we need to figure out the mean and the standard deviation of the difference between them. And so we are going to think about, well, how do we find the mean that is the difference between the two? We know with our rules for subtraction, so if we wanted to find the difference here, we're just going to simply just subtract our mean. So we'll end up doing 212 minus 230, and this gave us a mean of negative 18. Now down here, when we want to find the standard deviation of the difference, remember the little meme with the guy who says one does not simply add standard deviations? Well, also one does not simply subtract standard deviations. This is where we need to instead find the sum of the variances and then square root that. And the thing about this being a difference is that we're still going to add the variances. So that means that we're taking the individual standard deviations, we're squaring them, we're adding them together, and then we're going to do the square root. All right, so it should just end up being the square root of 31 squared plus 40 squared, and that gives us a standard deviation of 50.61. Okay, and then putting this onto our normal curve, so because our mean is negative 18, we'll go ahead and label that in the center. 0 is going to be off to the right, and we're wanting to find the probability that the difference is greater than 0. So we are going to shade to the right. Yeah, David.
Why do you do the square root here?
Right here for the standard deviation part. So if you look back at, like on the back wall from one of our 6.2 lessons, just the rule for getting the standard deviation of a difference, that's just what our formula is. And when we did the lesson that day, it was one of the days about the wages, and so we were looking at what we were doing is we were combining wages together. So like somebody had an hourly wage, and then we saw what happened if they got like a bonus, and so we were looking at what happened to the numbers by adding and subtracting, and we just saw through that experience that it just doesn't actually work to add or subtract the standard deviations. It had to do with the variances instead. So that's just one of our rules for combining random variables. Okay, and then we can just finish this out just like a Z-score table A or normal CDF type problem. So like I said, you will have a table A available for the Chapter 6 test. If you were to do it with the Z-score method, we can go ahead and take our value, which in this case would be 0. We're always going to subtract the mean, even if the mean is a value that's negative. So we're subtracting the mean, so it actually turns into plus, and then we'll divide by our standard deviation. And then this is where we get our Z-score, so it is a Z-score of 0.36. And when we go to table A here, because the shading is to the right, we want to make sure that we're doing 1 minus whatever the area is that we get for 0.36. So we'll go ahead and look that up here on table A. It looks like that area to the left of 0.36 is going to be 0.6406. So if we then subtract that from 1, that's going to give us the area that we're looking for. It's about 0.3594. All right, so let's take a look at part A. So it says, what is the probability that the first defective toaster is the 8th toaster tested? So this is one of those examples where probability of, like, when we're defining success, success is not necessarily a positive thing. Like in this case, a success would be a defective toaster. So from the problem here, we can say, all right, well, the probability that a toaster is defective, because it says that 2% are defective, it's going to be 0.02. And we want to know the chance that the first success occurs on the 8th toaster. And so this is one of those until situations. We don't have a set number of trials. We don't have a specific end value. We are basically testing them until they're defective. But we want to know the probability that it's the 8th one. So because it's an until, this is going to be a geometric setting. And so we can think about using our formula. So the probability that x is equal to 8, well, if it's geometric, that just means that the first 7 would not be defective. And so we're going to do 1 minus p, which is actually 0.98, and we'll raise that up to the power of 7. So it's going to be 8 minus 1 to get that first exponent. And then multiplied by the probability that it is defective, which is 0.02 for the actual 8th toaster. And really that would be 0.02 up to the first power. So the first 7 are not defective, the 8th one is. And so that ends up being about 0.0174. All right, so on our calculator, because this is geometric, to use the correct formula, this is going to be an example of geometric PDF. And the way that that gets filled in is it's just the probability value listed first, 0.02. There's no n. And then that's followed by 8, meaning we want to know the probability that the first defective one is the 8th one. And when we do that, you'll see that you get exactly the same answer. Okay, let's look at part B. So this is a little different type of question. It says, what is the probability that 10 or more toasters would need to be tested until a defective one was found? So here's this clue. Until we find a defective toaster, we don't have a set number of trials, so this one is geometric again. But now we're going to change the symbols that we're using because we want to know the probability that 10 or more would have to be tested. We want to find the probability that x is greater than or equal to 10. And that is going to be the same thing as 1 minus the probability that x is less than or equal to 9. In order for us to use a calculator function here, which I would definitely recommend the calculator on one like this. It's going to save us a lot of time. The calculator is always going to give us the total to the left of our value, and so if you think about our values, what 10 or more would actually look like. We'll draw a little line here, 10 or more. That's kind of like the shading is to the right. The calculator has the ability to give us the total of everything to the left. So 10 or more is the same thing as 1 minus 9 or less. And so to connect this to our calculator, this is going to be a geometric CDF problem. And the C always stands for cumulative, so that's going to give us the total sum of the probability of what if it's the first toaster that's defective, the second one, the third one, the fourth. It's going to add all of those up. And when we put it in, it's going to be really similar to what we did before, so we'll do 0.02, and then we're going to fill in a 9 over there for less than or equal to 9. See what you're there?
Very good. Now I know.
Yeah.
No.
All right, guys, so put in our calculator, we should get it's about 0.8337. Okay, is everybody good with those two? Sorry for the little pause. Yes, Elias. With the formula, doing it 9 times. Yeah, so what the geometric CDF is really doing is a shortcut of saying, okay, well, we're going to take the probability of the first effective toaster being the first one tested, plus the probability that it's the second one tested, plus the probability that it's the third one tested, all the way through the probability that it's the 9th one tested. So you could plug each individual piece into the geometric formula, which is just what we did right up here. So like the probability that it's the 8th toaster tested was this because of that formula. You could do the formula 9 times, add the result. That's going to give you this answer, and then subtract that from 1. So the calculator is just going to make that process faster, but all the CDF function is doing is it's just taking all the ones below it and adding them. Great question. Okay. Let's look at the next two. So in part E, now it says, if we randomly select 20 toasters for testing. Okay, so we're randomly selecting 20. So now we have a fixed number of trials. N is equal to 20. We want to find the probability that exactly one of them is defective. Well, the fact that we have that fixed number of toasters that we selected, that now makes this binomial. Now, because we're just finding the probability that exactly one is defective, we can go ahead and put that into our binomial formula. So our number of trials is 20, and we want to find the probability that exactly one is a success, which is defective in this case, so it's going to be 20, choose 1. The way that it was written on the AP formula sheet looks like this. And then that is going to be followed by the probability of success, which is 0.02, raised up to the power of 1. So we're saying we have exactly one that's defective. And then that's multiplied by the probability of failure, raised up to the power of 19. So the other 19 would not be defective. All right, when we put that into our calculator, we should end up getting 0.2725. Now, the other way that we can do this on the calculator to check, this is going to be binomial PDF, because it's for an exact number of toasters, exactly one toaster. And in here, it's going to be n, value of 20 listed first. Our probability P is second, and then we have 1 at the end, just like our K, or like our little lowercase x. And if you type that one in, you're going to see that you get exactly the same result. All right, and then let's look at part B. So now we are randomly selecting 20 toasters again. So n is equal to 20, so that's going to make this binomial. We want to find the probability that at most 2 of the toasters are defective. So the probability that at most 2 are defective, this is going to be that x has to be less than or equal to 2. Well, this is really the probability that 0 are defective, plus the probability that 1 is defective, plus the probability that 2 are defective. Now, we already know the probability that 1 is defective. That's what we did in the first part. This one doesn't have as many that we would have to check, so you could certainly do this with a formula. You can put this into the formula and get that result. You can put that into the formula, add them all up together. Or, in your calculator, you can do the CDF as a shortcut. And because this is already to the left, like think shading to the left, less than or equal to 2, we don't have to subtract this from 1. What we plug into our calculator is just going to look like this. And we should end up getting the same thing as if we would have done it by hand with a formula. It ends up being 0.9929.